Hello, and welcome to another micro tutoring session from Prep Plus. Prep Plus micro tutoring sessions unlock the secrets to common math and physics, homework, and exam problems. Today's topic is an advanced undergraduate topic in the solution of partial differential equations using the method of separation of variables. So the nice thing about today's problem is it combines physical intuition with the mechanics of the mathematical techniques employed in getting the solution. So let's get right down to it. Let's say the exam problem that you're asked to solve is to solve the one-dimensional diffusion equation. So this is called the diffusion equation, also called the heat equation. It describes the flow of some solute dissolving within some other material, which is just like the flow of heat through some material. So it's first order in time, it's partial differential equation, which is first order in time, second order in space, for the function u, which is a function of time and space x. It's partial differential equation. We have boundary and initial conditions. The boundary conditions for all times t at x equals 0 and at the end x equals L, this solution is 0, and the initial condition at time t equals 0, and for all locations x, the heat distribution is given by some function f of x that someone has just given to us. So first order in time, second order in space. K is some constant, which is often called the diffusion constant. We have our boundary conditions and our initial conditions. So let's just get right down to it. So first off, we're just going to make a guess that the solution is the product of two functions. One is a function of strictly of time. The other is just a function of space x. So we're going to guess a solution of the form t of t times x of x. So we're guessing a solution that is a product of two functions, capital T, which is just a function of time, and capital X, which is just a function of space x. So we're guessing this solution. So now let's just plug this guessed solution into our partial differential equation and see what we get. So we get x of x dt of t with respect to time equals k times t of t d2x with respect to x squared. So all I've done is plug in our guessed solution into our partial differential equation, and we get x times the ordinary derivative with respect to time of the function cap t equals k times the time function times the ordinary derivative, second order derivative of cap x with respect to x squared. So now let's just do a simple manipulation. Divide both sides by the product k times cap t times cap x. Nothing fancy. So we get 1 over t, k times cap t dt by dt equals 1 over cap x d2x dx squared. So all I've done is divide both sides of this equation by the same thing, k times cap t times cap x, and this is what I get. So now let's just look at this. The left-hand side is something that's strictly a function with respect to time, little t, and the right-hand side is something that is strictly a function of x, the spatial, little x, the spatial variable. So the only way that something with respect to x can equal something with respect to the only way something with respect to time can equal something that is with respect to x, the only way that can happen is if both sides of the equation equal the same constant. And we're just going to call that constant mu. So now this stuff is equal to mu, and this stuff is equal to mu. So now we've separated it into a problem with respect to time and another problem with respect to x. So now let's just look at those two parts separately. So now let's just look at the time solution, the time part of the solution. And we have, so we're just focusing on the time part. So we're going to have dt of t with respect to time equals mu times k times t. Okay, so this we recognize from ordinary differential equations. We can write the solution as something times e to the mu k time t. So the solution cap t is something times e to the mu kt. So now let's look at some extreme possibilities for the value of mu. Now if mu is 0, this is always going to be 1. And then so the time, let's make this explicit, the time function is only the something and has no time dependence. So we expect that the case mu equals 0, it's not going to be too interesting to us, so we're going to, that's just a trivial solution with no time dependence, so we don't expect that to actually be a solution that we're interested in. So now let's look at the possibility of mu bigger than 0. Mu is strictly positive, so then this exponential term grows without bounds. Now we know from physics, anything that's actually physical doesn't grow to infinity. So we expect the diffusion of some solute within some other material to not make the concentration of the solute grow to infinity as time goes on. We expect the concentration of the solute to be bounded as time marches on. So for that reason, we believe that the case where mu is bigger than 0, where mu is positive, is not physical. So we don't consider the possibility of mu bigger than 0 anymore. So it's not physical. So now that leaves us, so we've looked at mu equals 0, mu positive, that the only thing left is mu negative. If mu is negative, then this term decays exponentially. So the solution is going to be finite as time marches on. And so we're just, so that is something that, okay, now we're getting somewhere. So the only really physical interesting solution is where mu is less than 0. So that just means we're just left with figuring out what this something is. So we just apply our initial condition. Mu at time 0, u is just this function that's given to us, f of x. So for t equals 0, this is 1, so we're just left with something equals f of x. So let's just, so we know that the time part of our solution is f of x times our exponential function e to the mu kt. So let's just write that to the side here. We've got part of it equals f of x e to the mu kt. So we've got part of our solution so far. Okay, so now let's look at the spatial solution, the spatial part of the solution, the cap x of x function. Okay, so that's just this part. So let's just write that out. d2x, cap x, with respect to x squared equals mu times x. Okay, so we recognize this from our class in ordinary differential equations. This is, we're going to guess a solution e to the rx. We're going to guess that. So we're going to plug our guessed solution into this ordinary differential equation. So if we just plug in our guess, we get r squared e to the rx. I'm going to disregard any constants for the moment. R squared e to the rx equals mu e to the rx. Okay, we divide both sides by the same thing, and so r equals plus minus the square root of mu. Okay, now we already know from our arguments about whether mu is positive, negative, or zero for the time solution that we're only going to be interested in the case where mu is negative. Okay, so that means this is going to be plus minus I, which is the square root of -1, times the square root of the absolute value of mu. Okay, so now from our guessed solution, this means the solution is going to be of the form e to the plus minus I x square root of absolute value of mu. Okay, don't worry, we're getting to the solution. Don't worry, don't get too excited. So we're getting to the spatial part of the solution. So we know the solution is going to look something like this. It's going to have some dependence e to the plus minus I times x square root of the absolute value of mu. So now we know that this is a real physics problem. We expect the solution to be real valued. And from this, e to the plus minus I x square root of absolute value of mu, we know that the solution must be oscillatory. So a real oscillatory solution, oh, that's just like sines and cosines. So let's just write that. So this is, we're using the physics of the problem and our intuition to come up with the solution. X, the spatial part, is some constant C1 cosine of x square root of mu, absolute value mu, plus C2 sine x square root absolute value of mu. Okay? It's a real, we expect for a real physics problem to have a real solution, okay, that is oscillatory. Bam. Okay, so now what's left is to figure out what our constants C1 and C2 are. You guessed it, we're going to apply our boundary conditions right here. So at x equals 0, the solution is 0. X equals 0, the sign part is 0, so that goes away. X equals 0 just leaves us with C1, so that tells us, since this is equal to 0, cosine of 0 is 1, C1 equals 0. Boom. Okay, the other boundary condition for all times t at L, x at L is 0, so that means C2 sine L square root absolute value mu equals 0, which means L square root absolute value of mu is n times pi, where n is like 0, 1, 2, 3, just non-negative integers. So that means that mu, we finally got it. Mu, all we know so far is that mu so now all we know so far is mu is going to be negative, or the interesting mu's have mu negative, n pi over L squared. That's what the absolute value of mu is, okay? Great. So now we know what the solution is. C2 sine x times the square root of this thing. So we are going to so this leaves us with, so we're going to go ahead and write the whole solution right here. Sine x n pi over L squared times x. Let's see, is that right? Oh, sorry. Sorry about that. This is our solution, x times the square root of this n pi over L. So this is our entire solution. It's the time part times the spatial part. So that's it for today's micro tutoring session from Prep Plus. Prep Plus is your online solution for customized learning in math and physics for high school and college. I'm Rodney Green, the president of Prep Plus, and I invite you to contact me to schedule a free consultation. Please check out the website prepplusinc.com.